first of all, I have to thank the organizers and the sponsors. Even if, getting physically to the location would be so much more fun, as the pictures from the first day of the conference clearly indicate, attending even via Zoom was useful already, and I just hope that things only will get better. Now, I'm going to talk about quantum classical hybrid dynamics. And first of all, I have to disclose a possible bias, or actually the existing bias. I want this program in some specific sense to fail, and you will see why, hopefully, as we go on. So I'll talk splits into 4 parts. I'll start with brief motivation and requirements about this dynamics. Then I'll move to Hilbert space mixed dynamics, phase space mixed dynamics, and if there is time, I will say a few words about relationship of mixed dynamics and general relativity. So I don't think that we need much convincing. What are the reasons that we want to have mixed dynamics? Still, even if it's a bit preaching to the choir, it's worth pointing out. So first of all, we might want an effective description. So quantum mechanics is hard, classical mechanics is easier. So we just use it as a computational tool, and whatever theory or model we're using should be just good enough to describe the experiments. Now, if we say experiments, there is obviously also a quantum fundamentalist view of the problem, accepting separation of the world into classical and quantum parts. And I definitely do not want to enter into this never-ending discussion of where to put the von Neumann cut and so on. If we just want to use this mode of description, it's better if we can do this consistently, and mixed dynamics should do the job. And finally, we might want to investigate the question of a fundamental description. And I think the only real motivational problem is what if general relativity is not quantized? Personally, I do not believe in it, but as I'm trying to be a scientist, I don't want to be based on beliefs. And in the absence of clear experimental data, I would like to see this definite mathematical arguments pointing to it. Now, if we want to develop a mixed dynamics, which includes general relativity, and that means we're doing fundamental theory, this one better be not just good enough, but at least self-consistent logically and mathematically, and then good enough to match the current experiments. So we can split the story, or at least the set of requirements, maybe into 2 blocks. One, which is probably any theory should satisfy at least for some time. And the first is that if there is no interaction, our description should split into classical and quantum ones, whatever we are doing. Now, it would be perfect if marginals that derive from some mathematical quantity reduce into valid Liouville densities, and for the classical system, and valid quantum states for the quantum one. And here probably it's also a good place to point that even if I say classical mechanics, some people would call it classical stochastic. So I'm perfectly fine with probability distributions in Liouville densities at the level of mathematical tools, even in our classical description. And next consistency requirement, which is, I think, closely related to the scheme being experimentally good enough for long enough time, what I think conceptualized by Lajos Diósi in his quantization-dequantization approach, where if we treat the entire system quantum mechanically and then take a classical limit for what we take to be its classical part, our mixed dynamics gives approximately the same description. And obviously, the last approach or last point cannot be really implemented on something that we try to consider as a fundamental theory in absence of the unifying quantum mechanical theory. Let's add a few more things, desirable points. So if underlying classical dynamic system in its dynamics, is given by the Hamiltonian, or if everything is quantum, so quantum system is described by unitary evolution, then we would like to have classical quantum dynamics as non-stochastic. I don't know whether it's possible, but at least it's a criterion that is worth trying before throwing out. Another not perfectly well defined, but still quite. Sorry, Jonathan, I think there is a question. Oh, it's just hand.
No. Yeah, sorry, I did have a question. Why don't you demand that it's completely positive at each point in phase space? Why are you just looking at the marginals of the quantum distribution? Because surely at each point in phase space, it needs to be positive rather than just positive on after you trace out the phase space.
I think you're right. I don't mention it here for very trivial reason that I don't think that I've actually enforced it when I was getting to the paradoxes that I like. So as as a quantum fundamentalist, I give to the opposition as much power as possible. If I can crush them, then that's fine. I think you're right, but I think it's a strong. But as it seems to be a stronger requirement, if some construction fails without it, then it will fail. But yes, you are right.
Okay, so you would consider it a minimal requirement?
Yes. It's just
that your dynamics doesn't have it.
It's just I wouldn't be using that in the following, so then it would be more for beauty than for actual implementation.
Okay, so the dynamics you present doesn't satisfy that?
Yes. Yeah.
Okay, and by
it's bad enough even without checking that.
Okay.
But you see, you're forcing me to reveal things that I wanted to keep it there.
And agreement with quantization, how much agreement? Do you mean anything specific by that, or is it just in general?
Again, it's at the moment I keep it vague because again I'm not using it in a precise form. But sure, I mean it's not a fully consistent list of, not exhaustive list of requirements, but just a sort of a list of reasonable things that we expect. All right. So, and again, if reasonably vague things like correspondence principle between classical equations of motion and quantum equation of motion at least holds, then it would be nice to have something like that in the case of the mixed dynamics. Of course, this is a bit more of an aesthetic requirement, I'm afraid, because the bottom line is almost like shut up and calculate. If we can get reasonably good probability distributions that approximate reasonably well reasonable Gedanken experiments, then we're probably fine. But those requirements moved me and the many collaborators, starting from of course Asher Perez, to try several approaches. The basic idea is that it will be good to combine objects of the same mathematical nature. So on one hand, we can try classical quantum Hilbert space approach, starting, let's say, from Koopman, von Neumann, Sudarshan. On the other hand, we might try quantum classical phase space, starting from Moyal's work. At least those approaches, no matter what else, they provide us with a natural split into classical and quantum parts. They do have deterministic evolution. They take in probabilistic initial data, and they allow to describe measurements and unsharp measurements. So at least some of the desired features we're getting for free. How much else, how many other things we can get We will see. So let's start with classical quantum Hilbert space, and we'll begin with actually classical Hilbert space. The starting point is the Liouville equation, which we can suggestively write in the operator form. Then we introduce Hilbert space. First of all, we introduce the wave function, which we, for simplicity, take just as a square root of the Liouville density. Then we have to introduce operators and observables, position and momentum. And for the classical system, in the classical system, from now on, all those generalized position variables are x's, and generalized momenta are k's. They are just multiplication operators. Then again, to write our operators, we need unobservables, and those are shift operators. Say px conjugate to x and pk conjugate to k. And the evolution has now form of the Schrödinger equation, but of course, oh, sorry, it's a wrong mathematical statement. Looks suspiciously like that, but of course, differential operators on the right-hand side are of the first order. The evolution is unitary, and the inner product between our wave function is conserved. Now, of course, this description is fully equivalent to the normal classical mechanics. So if we convert initial Liouville density into this classical wave function and evolve it according to the Liouvillean dynamics, and then go back to the Liouville density, well, probably maybe taking absolute value, we get the same result as if we would be evolving the Liouville density by the Hamiltonian. We can develop the Heisenberg picture. We can develop projectors and describe measurements, sharp, unsharp. Now, this is, of course, not a unique way of doing the dynamics. We can have more sophisticated gauge covariant Liouvillean dynamics, and this reference is just one, but still describes the situation pretty well, and I'm going to borrow some of the results from it in a moment. Well, so we have Hilbert space for classical mechanics. Now, for the combined system, we just combine Hilbert spaces. In quantum mechanics, again, we have a Hilbert space for free. So our combined wave function is the function of x and k, and quantum configuration variables q, their conjugate momenta are p, and maybe some discrete quantum variables like spin. So, of course, this wave function can be written as a superposition of direct products of classical and quantum wave functions. The dynamics on this combined Hilbert space should be given by, let's call it the Hamiltonian, which involves, well, essentially Liouvillean on the classical part, a Hamiltonian on the quantum part, and the interaction term. And again, we can describe projectors, we can develop measurement formalism, we can discuss quantum classical entanglement, and we have two pictures: a Schrödinger picture where we evolve the wave function, and the Heisenberg picture where we evolve the operators. Of course, the important question is how to write the interaction term, and that brings some interesting non-trivial issues. So again, we assume that we write it as sum of product terms with operator acting on the classical side and operator acting on the quantum side, and at least a simple-minded approach, which is the simplest possibility if you want to satisfy Jacobi identity, is that each one acts in its natural way on its own side. So the Liouvillean bit is constructed from some classical Hamiltonian-like entity and operates by applying Poisson brackets, and the quantum bit just acts as operators should act on quantum mechanical object. Again, there are more sophisticated derivations and more sophisticated approaches to that. I'm sticking to the simple one. And let's take an example where it works wonderfully. Was very curious that the same system that I once considered in proposal for my thesis and then dropped was actually evaluated in great many details in a paper by Bonder, Guy, Balmas, and Tronci, which was very nice to see and very educational to learn its properties. So with our definitions, the Schrödinger equation is rather straightforward. The system can be solved, well, pushed as much as possible analytically, and then there are numerical results starting from factorized initial, say, oscillator and spin state, setting particular values of parameters and particular value of initial parameter for the wave function. We get interesting evolution of the blob in the phase space, and also interesting evolution and sort of developments on the Bloch sphere of the spin, which also indicate a build-up of periodic evolution, so of entanglement between classical and quantum parts, which is again very interesting feature to see explicitly. So we do have unitary evolution. We have quantum classical entanglement. Unlike Alexandrov Gerasimenko approach, we don't have stochasticity, and such systems and similar ones can be successfully used, for example, for description of the Stern-Gerlach experiment. Okay, so far so good. Now let's try to cause some problems. And the problems again will be related to the issues with identification of our interaction term. So if in our overall classical system, the interaction is just coupling of classical position and quantum position, the Hamiltonian, the Liouvillean Koopmanian operator should involve momentum, which is unabsorbable momentum, which is conjugated to the classical position. Now, a benefit, Jacobi identity is satisfied. So, however, we can get into some trouble, or at least some apparent trouble first. Let's look at two coupled harmonic oscillators where the coupling again is linear. And actually, I have to admit that harmonic oscillators until almost the very end will be the main workhorse and the main example in my talk. So equations of motion, classical and quantum, look identically. The only difference is that for quantum equations, you need to put hats on the top of the letters. However, quantum mechanically, the situation will be different. So the operator has momentum, and as a result, equations of motion, well, first of all, acquire equations of motion for the unobservables, which is not a big deal in itself, but the unobservable operator gets into the equation of motion for the observables. That is unpleasant regarding the correspondence principle. And this is also bad because the nice sweet pair of unobservable operators essentially get solutions in terms of sines and cosines, and then they pump up as an external force the observable momentum and lead to blow up of the energy. Essentially, because the spectrum of the Liouvillean operator, which is like say angular momentum operator, is unbounded. So that's bad, and we would like to avoid this trouble. So let's see what are legal possible couplings, at least according to the rules of the game that we have. So again, let's take two harmonic oscillators. I put bar on the variables so they are dimensionless. So we'll already rescaled by their characteristic lengths. Their commutators are just I. The rest of the commutators are 0. It's a bit more convenient to do the analysis in terms of creation and annihilation operators, both normal creation and annihilation operators for the quantum part and creation and annihilation operators for the classical X and K part. Then we can think about the more general bilinear interaction term, which looks somewhat ugly with a number of terms. And we say, okay, we don't want unobservable operators being coupled to the observable ones. It reduces the number of coefficients. So those will be the equations for of motion, of Hamilton equations for the system where nothing unobservable couples to observable operators. The situation is still not perfect because we're still going to have resonances unless we kill this. And at the end of the day, we're getting that the interaction term should look like some function of X and Q only. The result, which also appear, I'm not sure whether it was explicitly stated as the only possibility, but that's the case that considered in the papers I cited before. So we don't have resonances, which is good, but we don't have a clear analog to purely classical or purely quantum system in such a way that those analogs will satisfy Jacobi identity. It looks like a problem. I'm not sure if it's really a problem. What it definitely not showing that mixed dynamics is impossible. Mixed dynamics in strong sense that satisfies all those extra wishes still not dead. And we can see it if we go to the phase space. So let's look at the quantum mechanics in phase space. The basic object in this case is the Wigner function. Dynamics is described in terms of the Moyal brackets. Again, Moyal brackets, generalization of Poisson, they obtained in this operatorial expression. Starting from the star product, because of the sign that you see here, they sometimes called sign brackets. Using the dynamical equation in terms of Moyal brackets, we again have identity between quantum calculations and classical calculations. What's, again, I think everybody knows, but it's useful to remember that Wigner function, while it's a quasi-probability distribution, and while it has a lot of useful properties, it can be used to calculate expectations and correlations, and its marginals give positive probability distribution, say, for position on momentum. By itself, it might be negative, and even superposition of two Gaussian states, for each of which the Wigner function is non-negative, will have a negative bits. Writing the star product for the case of more than one variable, we get a rather ugly looking, but I'll say computationally manageable expression in terms of series in partial derivatives. And it's important to realize that it has some very neat relations with the Poisson brackets. So first of all, correction to the Poisson bracket starts at the order of h squared, which is nice and gives some leeway for semi-classicality. And more interestingly, if we deal with quadratic Hamiltonians, then Poisson brackets and Moyal brackets are the same. Immediately follows from the definition, but somehow I wasn't aware of it for a while, that Quadratic in this case means that each variable should be quadratic. We can have cubic terms, so let's say q squared x, and we will still have Moyal brackets coinciding with Poisson brackets. Now, that definitely should indicate that linear coupling of oscillators is not a problem. So actually the answer is yes and no. Again, the question is how much from classicality you are ready to sacrifice. So we start with the phase space. Now, phase space of the combined system. We want to impose on it or construct on it legal kosher Wigner function. Its marginals would be giving us Wigner function for the quantum system and Liouville density for the classical one. Again, nobody guarantees that it will be positive. In this case, we'll have a disaster. But for oscillators, we should be doing okay. And we'll run the dynamics via Moyal brackets. In quadratic case, it's definitely possible. We might try some interesting, weird propositions in a general case. Nevertheless, let's see an instructive example. Example was considered by Barcella, Carballa, Rubio, Garay, Gomez, Escalante. Again, coupled harmonic oscillators, linear coupling. What they considered as a slightly trollish example, the classical probability distribution is just delta. So it's exact, single point in the phase space. And the Wigner function, the good Wigner function, which corresponds to a valid quantum state of minimal uncertainty. Coupling, numerically, we can investigate what happens to various correlations and variances and cross correlations. I'm just copying two pictures for two different sets of frequencies, or more importantly, different relations between frequencies. And what we see that there is trade-off between uncertainties in classical and quantum parts, and quantum uncertainty, at least alleged quantum uncertainty, might go lower than what is permitted by uncertainty relations. It's a problem, but not a big problem. We can figure out what to do. Just force classical probability distribution not to be a delta, but contain enough initial uncertainty. It actually can be put on a very precise footing in a paper by Bartlett, Rudolph, and Speckens, where they considered epistemically restricted Liouvillean mechanics, which is essentially classical mechanics, say Liouville functions, which are sufficiently wide to saturate the quantum uncertainty relations. In this case, they showed that it's equivalent to the Gaussian mechanics and the Gaussian quantum mechanics. And that means quantum states, which are Gaussian, that means Wigner functions are Gaussian, quadratic Hamiltonians, and that in this case, it's overall quadratic, no, not more than that. And initial uncertainty. In this case, the picture on the left, which is unacceptable, is not going to happen. And if we measure uncertainty for the quantum system, it always will satisfy uncertainty relations. They used it for interesting arguments about quantum foundations. For us, it just tells what to do. Pick up sufficiently wide uncertainty for the classical system when you load it. Then we might even venture to get a modified star quantum classical product, where the quantum one is the full one and the classical one is, well, just the Poisson bracket. In this case, I don't know if we really can resolve any of the issues. But it looks like we don't have to, because we still can create rather interesting problems. So let's again take coupled to two harmonic oscillators. They're coupled, but they're coupled in this particular way. Moyal brackets are still Poisson brackets. So quantum dynamics and classical dynamics are exactly the same. Now let's try and break the system. So the easiest way that we found in analyzing it, and by breaking the system, the original motivation was to start with a kosher state and end up with quantum system violating the uncertainty relations. Dynamics is not very easy, so we just calculated various correlations. The approach was take initial Gaussian overall state, quantum classical, with admissible correlations between classical and quantum systems. Then, and I think now that's the weakness of our work, we use just classical interpretation. So we were taking the resulting overall Wigner function as Liouville density. It's probably not right. And then we were checking classical correlations, not classical correlation, classical variance, only, my bad, quantum variance, so only P and Q, two quantities. And we're finding that by doing series expansion, that within time t star, which depends on the initial correlations and also coupling strengths, uncertainty relations are violated. It would be very nice to shout that that's a problem, but our initial conclusions in the paper were a bit too hasty. The overall W, the overall Wigner, is not guaranteed to be Gaussian. So we cannot really, our problem just indicates that we cannot take its quantum marginal and use it as if it was the Liouville density. So we just have something interesting happening to the Wigner function. However, if you look at the problem, at the Hamiltonian and the dynamics, it's expressed in a totally symmetric way. So we can reverse the roles of classical and quantum systems. And what we get is that now classical correlations, which were initially above the quantum uncertainty relations, now go below it. By itself, it's also not a problem. However, we're getting this result because the Wigner function has some properties which are legitimate for the Wigner function, but forbidden for the Liouville density. Maybe it becomes negative, or maybe not, just too narrow. In this case, what we can do, we can play a bit of a cheating game. We can consider those betas to be time dependent. We keep them constant. We bring our classical system below the quantum uncertainty relations, and then change, for example, the coupling to the linear coupling previously considered. And that,
Daniele, you have 10 minutes including questions.
Perfect, thank you. And then we know that if we're under quantum bound for the classical uncertainty, it will be transferred to the quantum system and will produce illegitimate quantum state. So the thing, as much as it looks promising, dies if our coupling is nonlinear. So just a few slides which I'm going to cover, because unlike previous work, It's not a done thing, but more like a bunch of ideas. So what do we want from general relativity? The question is, of course, why to quantize gravity? I think Jonathan Oppenheim is going to talk about it. The discussions are ancient. Foundational arguments maybe go to Epley and Hanna. Again, quoting Oppenheim, the best trolling in the history of PRL was the paper by Page and Gaekler, which was actually a report of the experiment. I have quite a lot of things to say about this experiment and how to make it more trolling, but that's a different story. Again, there are arguments why modify quantum gravity and the black hole information loss problem plays a role in it. I prefer not to say anything because if I start, I'm not going to stop in any reasonable amount of time, and I really will have to cut off my Zoom link. So let's just ask the following question. That's my bias. That's why I'm really curious to see mixed dynamics to fail. Mixed dynamic, of course. Mixed dynamics for practical people. Mixed dynamics in real life, good for all practical purposes. It works. Why am I saying mixed dynamics fails? Only the one which purports to be and aims to be the fundamental theory. So can we exclude deterministic classical general relativity quantum metadynamics? And I don't know. I think a useful setting is as follows. So we start with a probably simplest system. So we take Einstein's equations of general relativity with source matter with a linear massless field. That's our Einstein equations. Then we rework them in the equivalent form, but this equivalent form is suitable for the post-Minkowskian expansion. Again, there is vast literature on the subject that I don't have to quote. The end result of this transformation is that we get a wave equation for the corrections, so for deviations of the metric from the flat space-time, and the operator is the flat operator. On the right-hand side, we have energy momentum tensor, which has slightly horrendous form, and I'm deliberately not writing what are those additional terms are, but it's enough. I mean, if you really want to, I can show you the slide, but better not. The point is, however, that they're quadratic in H. They're quadratic in this perturbation. And then we impose box normalization or quantization, if you want to quantize our field. And what we get bunch of harmonic oscillators formally on flat space-time, something that we know. And sorry, with quantization of flat space-time, we get just again bunch of oscillators. People who do proper post-Newtonian analysis, post-Minkowskian analysis, expand H in powers of J. If we look at the sort of schematic structure of equations in power of J, we get this left-hand side of the Einstein equation, right-hand side, which is where we get terms of from the energy momentum. And this is, again, the equation for our oscillator, for our field. So what we're going to get if we cut at some reasonable order of approximation, just uglier systems of coupled harmonic, non-linearly coupled harmonic oscillators that we've seen before. And if a previous scheme fails, we have grounds to believe that it will fail also here, and we cannot have deterministic quantum classical dynamics. That's essentially it. So let me quickly run through a summary. So Hilbert space approach, elegant, very useful to describe measurement, works in some cases, comes with some baggage, and possibly not suitable to represent a universal fundamental theory. Phase space approach, on one hand works in some cases where a Hilbert space approach doesn't, has quite a number of interesting problems. Again, probably not good enough as a universal theory. Now, should we quantize general relativity? A honest answer is I don't know. First, even if we're going to buy and accept per face value the statement that fundamental mixed theory is of the type I wanted is impossible, it still leaves open. It leaves open possibility for the stochastic dynamics that, for example, was popularized by Oppenheim. In addition, we also have to admit that since there is no isomorphism or equivalence theorem between the approaches, failure of the approach may indicate not the failure of the entire idea, but just a failure of imagination of the one who was proposing in the first place, and somebody smarter can come with a different scheme. Now, personally, I would like to quantize gravity. What happens in real life, I honestly don't know. So thank you for your attention.
Thank you very much for this beautiful talk. So we have time for a couple of questions. Maybe Cesare, do you want to start?
Yeah, thank you for your talk. I am really glad to see that this work we have done has stimulated people to go through the actual calculations. And I was particularly glad to see that you studied the problem of the coupled oscillators, which we also studied. I have to say, you got a bunch of equations there, but you made a mistake in the way you presented this material. Because when you wrote the equations of motion for the Q's and the P's, in this context that we developed, and then of course, you know, if you have in mind different interpretations, it's fine. But in the way we worked it out, the classical observables are not just the Q's and the P's; they are pre-quantum operators. So in order to actually study the evolution of the classical subsystem, you should look at the evolution of the pre-quantum operators. Now, we did that. We did that in two different ways, actually, two different but equivalent ways, just to check that the equivalence would stay. And these two ways were the Heisenberg picture as well as the Ehrenfest theorem, the quantum classical Ehrenfest theorem. We got exactly the same answer, and actually, the Ehrenfest equations look formally exactly the same as the purely quantum case. So there was no problem there.
No, it just makes it just clears that the naive approach, and I should have said it more explicitly at the beginning, fails. More interesting one stays, and that's. Again, good to know, and that's something that I will be planning to look into in more detail.
Great.
So again, thanks, and
have more correspondence.
Thanks for actually spelling it out.
Yeah, we should be in more contact. Thank you.
Let's take a second quick question, maybe by Marcel Zilato.
Yes, thank you. First, Daniel, thank you for this wonderful talk. I appreciate the clarity, and I appreciate also the fact that you're very clear about the fact that you have model dependence in hybrid systems. That is, you have to really look at the Hilbert space approach, you have to look at the phase space approach, and so on and so forth. I just want to maybe put a plug in for my talk later. There I will present a third approach, which hasn't been discussed in the meeting, which overcomes many of these problems. And it's a different mathematical space, and it's a different way of coupling. And just one should keep that in mind. But as I said, you were very clear about that. And I also appreciate very much the calculations, as also Cesare said. Another quick remark regarding the quantization of gravity. I'm in agreement that it would be very nice to see it quantized. I'm skeptical about the proofs based on thought experiments about that you need to quantize gravity. And the weakness that I see is that essentially any statement of a thought experiment already includes a hybrid model. That is, you have to specify the coupling between the classical sector and the quantum sector. In the case of the experiment you mentioned, there is a gravitational wave in the classical particle. And this is where there's a lot of loopholes. And it's just a remark. Yeah.
Again, I have to say that I agree with the remark. And that's why actually, I would, and probably then expanding on it, I would say that trying to build a mixed dynamics model for such case is probably the only way to make those arguments, whichever way they go, logically consistent.
Yeah, and the what I will show this afternoon, I will just mention it without showing any calculations. It is possible to extend to fields, so one can look at the gravitational field coupling to quantized matter fields.
Again, that will be very useful. Unfortunately, I will be not watching it in real time.
Okay.
Because it's already 6 here.
I understand. Yeah.
But recordings are available, and I'm looking forward to it.